Welcome to the first part of the problem-solving session for Chapter 11. Let's begin with question 1, which states, if a torque is acting on a particle about an origin is 0, in other words, if the torque that acts on an object is 0, what can you say about the object's angular momentum about the origin, about that point? Well, let's see. They tell us that the torque at that point is at the origin is equal to 0. But the definition of torque is given by the rate at which the momentum of an object changes with respect to time. So if the torque is 0, that implies that the rate of change of angular momentum with respect to time is equal to 0. And that can only mean that the torque, the angular momentum, must be constant in time. In other words, it does not vary in time. Well, this isn't much different than the ideas that we had back in Chapter 9 when we said that the force is given by, in other words, Newton's second law can be given as the time derivative of momentum, okay? And if that was equal to 0, if there was no external force acting on an object, that implied that the angular linear momentum was constant in time. And this allowed us to work with conservation of momentum in the case where there were no external forces. Here, we're dealing with conservation of angular momentum in the case where there are no external torques. And this will allow us to look at momentum before a transformation occurs, so some interaction, the angular momentum of a system as it interacts before and after, and be able to state that as long as there's no external torque, that the angular momentum before the interaction should equal the angular momentum after the interaction. Okay, question number 2. A particle of 1 kilogram is moving in the xy plane in a circular path of fixed radius r. It has a constant speed, 3 meters per second, but of course the speed portion is constant, but the direction is not, because this particle is undergoing uniform circular motion. In any case, we're asked to determine the magnitude and direction of the angular momentum. So let's begin with the magnitude of the angular momentum. We know that that is given by, well, let's write the general formula for angular momentum. It's r, the radius vector from the point about which the rotation occurs to the actual object, cross p, where p is the mass of the particle times its velocity. So in other words, its linear momentum, mv, is going to be crossed with r, or r cross mv. And the rotation, you can see, is occurring in a counterclockwise direction, which means that we are going to have, if we use the right-hand rule, r cross v, we sweep our fingers in the direction of the rotation, and you can see that the direction of L, okay, is out of the plane of the paper. In other words, as you sweep your right hand by the right-hand rule, the forefingers sweep in the direction of the rotation, and the thumb points in the direction of the vector, which in this case is the vector angular momentum. So the direction of L in terms of direction is out of the plane, okay, out of paper or out of plane. And the magnitude is going to be the magnitude of r times the magnitude of mv times the sine of the angle between r and v. What is that angle? 90 degrees. So here the theta is 90 degrees and the sine of theta is equal to 1. R is equal to 2 meters. V is equal to M is equal to 1 kilogram. V is equal to 3 meters per second, and that gets multiplied by 1. So you can see that the magnitude of the angular momentum is going to be 6 kilograms meter squared per second. Okay, next question. A 2 kilogram particle has a position vector given by r equals 6i hat plus 5t j hat. We're asked to determine the particle's angular momentum about the origin as a function in time. So L equals r cross mv. Well, we've been given m as 2 kilograms. We've been given r. What about v? No problem. We know that v, the velocity of the particle, is equal to the derivative of its position function with respect to time. And when we look at this expression here, it's merely 5 meters per second in the j hat direction. So in other words, the derivative of r with respect to time gives us 5. J hat direction is the direction, and meters per second is the unit. So now we're prepared to consider the cross product of 6i hat plus 5t j hat, that's in units of meter, cross 2 kilograms multiplied by 5 meters per second in the j hat direction. Or in other words, we're going to cross r with 10 kilogram meters per second in the j hat direction. Okay, let's see. 6i hat cross 10 j hat gives us 60 for the number part, 6 times 10. The I hat cross j hat, if you recall from our cyclical permutation, I cross j gives us a k hat. Okay, so this will be the unit kilogram meters squared per second in the k hat direction. Next term, 5t j hat cross 10 j hat. J hat cross j hat is 0. So here the angular momentum is simply 60 kilograms meters squared per second in the k hat direction. So in fact, this angular momentum is constant. There is no t dependence whatsoever, which means that for this given particle with this particular position function, the angular momentum does not have any time dependence and therefore has a constant value of 60 kilogram meters per second squared. All right, next question. Here we're told that the mass of a bowling ball is 6 kilograms and has a radius of 0.12 meters. The ball is rotating at 10 revolutions per second. Beware that this is not an SI unit, and so if we truly want its angular speed, we have to take 10 revolutions per second, multiply that by the relationship that 1 revolution equals 2 pi radian. Here you can see the conversion eliminates the rev, and so omega is equal to 20 pi radians per second. Okay, assuming that the ball is a solid sphere with no holes in it, what is the moment of inertia as it rotates about its axis? Well, if this is a solid sphere of uniform mass, then we know that the moment of inertia is given for a solid sphere is given by 2/5 m of the bowling ball times r of the bowling ball squared. When we substitute the values, we get the moment of inertia is 3.46 e to the minus 2 kilogram times meter squared. What is the ball's angular speed? Well, we've already calculated that. In radian per second, it's 20 pi, oops, we neglected our pi here, very important, 20 pi radian per second. Using the information above, calculate the ball's angular momentum. Well, the angular momentum, as you can see here, will be that component in the z direction. That is the direction of angular momentum. And here it's merely given by I times omega, which, by the way, omega is also in the z direction. As you can see by the right-hand rule, when we take into account the rotation, fingers sweep out the rotation, the fingertips would be moving in a counterclockwise fashion, as indicated here, and the thumb would point straight up. Well, take I, the calculated I, and multiply by the omega, which we just worked out as 20 pi radian per second, and that gives us an angular momentum in the z direction of 2.17 kilogram meters squared per second. Okay, last problem in this part, part 1. A father and a daughter sit on opposite ends of a seesaw. Model the seesaw as a rigid rod which has a mass of 50 kilograms and a length of 6 meters. And we're going to say it's uniform so that its weight happens to be at its center of gravity. So here, 50 kilograms times 9.8 Newton, 9.8 meters per second squared gives us the weight of this board as 490 newtons. Okay, well, this board is rotating in this direction, which is shown to be counterclockwise, and we're told that the speed of rotation is 5 radians per second. The question is, determine the total moment of inertia of the system. What is the system? The father, the board, the daughter. Okay, each will have a moment of inertia, and the rotation is about the center of the board. Well, we're going to take the father's moment of inertia to be mf, the mass of the father, times his position relative to the axis of rotation, which is L over 2. Then we're going to take the daughter, which is squared, right? Mr squared. So here we're trying to find the total moment of inertia, okay, of the system, in other words, okay? The mass of the father times his distance squared to the axis of rotation, the mass of the daughter times her distance to the axis of rotation squared, plus what is the moment of inertia of a rod that rotates about its center of mass, I ask. And if you remember from chapter 10, 112, the mass of the board times its length squared. Okay, So now see, we're incorporating all the ideas from previous chapters. Let's see if we can plug in some numbers. The mass of the father times L over 2 squared. The first term is 630 kilograms meters squared, plus the mass of the daughter times length over 2 squared gives us 270 kilogram meters squared, plus 1/12 mass of the board times its length squared gives us 150 kilogram meters squared. So effectively, I of the system is equal to 1,050 kilogram meters squared. Okay, so we have the moment of inertia of the system. The next question asks us to determine, so this is part A. Part B asks us to determine the angular momentum of the system, magnitude. Okay, just the magnitude here. And here we know that the direction is going to be along the z-axis. And because the rotation is counterclockwise, it'll be the positive z-axis, in case you were wondering. All right, well, let's see. We need I, that which we just calculated for the system, multiplied by omega, which, by the way, is also along the z direction based on the rotation. So we take 1050 kilogram meters squared multiplied by 5 radian per second squared, or radians per second, excuse me, and we get 5,250 kilogram meters squared per second. That's our angular momentum. Next, we're asked to determine the torque of the system as a function of theta, the angle theta. Now, to do that, we have to come up here and see about where this rotation is occurring. And you can see that this is not an equilibrium problem, and because the rotation really does occur. You can see the father is rotating downward in a, let's see, in a counterclockwise direction. The daughter is rotating upward in a counterclockwise direction, and so these are true torques. Well, we need to consider the net torque and later consider what the angular acceleration is, because the clockwise torques are not going to be equal to the counterclockwise torques. In fact, we see that we have a net counterclockwise torque. So this is unbalanced torques, which means rotation is occurring. The rotation is occurring about the center of the board. So we have to determine, if this is the line of force of the father, we have to determine the D of the father. We have to determine the D of the daughter. Okay, in other words, their moment arms. And you can see this is also L over 2. Okay, so for the daughter, we have L over 2 cosine theta. See, this is the side adjacent. That is perpendicular to the direction of the force. But this is also theta, and therefore the father also has a moment arm of L over 2 cosine theta. And so, in fact, it's the father's weight that is causing the net torque. So here we have mg of the father. Now, when we take his mass multiplied by 9.8, we get 686 newtons for the father's weight, times L over 2, which gives us 3 meters cosine theta, plus, plus we have the weight of the daughter, which is 294 newtons, times her moment arm, which is 3 meters, times the cosine of theta. And let's just review that we do have clockwise, and oh, actually, this is counterclockwise. Excuse me, towards the axis of rotation. This is clockwise, except that the father's torque will be greater, which is why there is a net counterclockwise. Yes, that's correct. Forgive me, because it's the force toward the axis of rotation. So there is a clockwise torque, and this will become negative since this is the clockwise rotation. But because the counterclockwise torque is greater than the clockwise torque, there is a net counterclockwise torque. So, having said that, we get a net torque of 1,176 cosine of theta, and then the last part says if theta was 37 degrees, what would be the torque, the net torque? And you can see the net torque then would be 176, and by the way, the unit here is the Newton meter, 1,176 Newton meter times the cosine of 37 gives us 939 Newtons meter. If we are trying to determine alpha, we take the net torque, 939 Newton meter, which by the way would be considered positive since it's a counterclockwise, and we would divide it by the moment of inertia, 1,050 kilogram meter squared, and that should give us a value of 0.89 radians per second squared. Well, this concludes the last part of the problem solving session for Chapter 11. Until next time.